Our task in this video is to linearize the given unpaused nonlinear parametric state space model about an equilibrium point. So it is unforced because, as you can see from equation 1 and 2, that is the state space equations, there is no input applied to it. So since we are linearizing about the equilibrium point, our first step is to find the equilibrium point. So a system is in equilibrium if the summation of the input acting on it is 0, and if that is the case, then the rate of change of the state is 0. So applying this to equation 1 and 2, so from equation 1 we can see that if S1 dot is 0, so it means our S2 is equal to 0. So applying the condition of equilibrium to equation 2, we can see that if S2 dot is 0, then it means minus gamma sine x1 minus beta S2 is equal to 0. But for equilibrium point, we have already found out that S2 is equal to 0. So substituting it into this, we'll have minus gamma sine x1 is just equal to 0. So it means sine x1 will be equal to 0. So my x1 will just be arcsine of 0. So for arcsine of 0, we have multiple points. So we have 0, pi, 2 pi, 3 pi, and several multiples of pi. So from this solution, you can see that for S2, I have a single point which is at 0, but for S1, I have multiple points. So it means I will have multiple equilibrium points. So denoting my equilibrium point as S1 naught and S2 naught, it means I will have different combination. So I may have 0, 0. So for S2, it is constant. So I may have pi and 0. I may have 2 pi and 0, and so on. So I can linearize my nonlinear model around each of these points, since the question just say linearize the model about an equilibrium point. So now I will linearize it about this first point, that is when S1 is 0 and S2 is 0. So as stated, this is the equilibrium point I'm using for my linearization. Equations 4 and 5 give me the linearized model that is obtained from Taylor series expansion. So change in x is just the deviation of the state from the equilibrium point, where A and C are just my Jacobian matrices. So these are my Jacobian matrices, and they are computed using the partial derivatives of the given functions and about the equilibrium point. So from equation 1, we can see that f1 it is just equal to x2. So the partial derivatives of f1 with respect to s1 is just 0 because I don't have any x1 here, and its partial derivative with respect to s2 is just equal to 1 because I have f1 is equal to x2. So going to the second one, I know that I have my f2 is equal to minus gamma sine x1 minus beta x2. So my f2 with respect to x1 will just be equal to minus gamma cos x1. However, I need to substitute the value of x1 for the equilibrium point, which is 0. So cos 0 is just equal to 1. So I know that my the f2, the x1 will just be equal to minus gamma. Now finding the C matrix, I know that my H is just equal to x1. So it means my the x1 is just equal to 1, and my the x2 is just equal to 0 because I don't have any x2 there. So substituting the values into my matrices, I will have the f1, the s1 is just 0. Then the f1, the s2 is 1. Then I have minus gamma, and I have minus beta from here. So for C, Jacobian matrix, I have 1 and I have 0. So finally, this is my linearized model where gamma and beta are parameters of the model. So if you want more tutorials on control systems, watch the playlist on the screen. Please like and subscribe to the channel. Thank you for watching.